Okay. It's been a little bit since I've recorded something, but let's see if this works, and hopefully this will be helpful. Okay, so one of your classmates sent this in and is asking about this, and I know we didn't get to spend enough time, so let me walk you through it. Actually, I didn't even read it. I just glanced at it. For a 4-unit class like statistics, students should spend an average, oh my goodness, and I didn't write the question, sorry, an average of 12 hours studying for class. So they're talking about that being the mean, and then they explicitly tell you that mean of 12 hours down here at the bottom of the second sentence, the end of the second sentence. A survey was done on 21 students, and the distribution of total study hours per week is bell-shaped, meaning it's a normal curve, with a mean of 12 hours and a standard deviation of 2.6 hours. So they're telling you that it looks like this. When they say it's bell-shaped, where the curve, the distribution is normally distributed, it's something that looks like that. It's not exact. My drawing's not exactly nice, but close enough, I think. And maybe that's not quite in the middle. Let's shrink it over just a tiny bit. Let's see if I can. Again, I'm more used to a different piece of software. Can I just drag it? Yeah, there we go. That looks a little better to me. Okay, it's not really the y-axis. The y-axis is way over here. But this is the axis a line of symmetry. Okay, fold the curve in half or fold the paper in half, and the right side will lay right on top of the left side. Again, my drawing's not very nice. This is the number that is the mean. This is the mean. It's always going to be in the middle, and that value is 12 hours, or 12 hours per week. Okay? And they didn't put the week part in, even though they said it in the beginning. They didn't put it there at the back end of the second sentence, so 12 hours. Now, since it's normally distributed, we can calculate a standard deviation of 2.6 hours. And so this empirical rule is telling you the density of each section of this curve. So when I said yesterday that this seems a little bit out of place because we haven't talked about what a distribution function is and what it's telling us, I'm going to have to tell you now, which is fine. A distribution function is basically talking about, I tried to talk about it in class when we had all the baby weights in the middle. Any future classes that I use this video on, you're not going to know I'm talking about baby weights, but the very heavy babies, 11-pounders, are out here because there are only a few of them. They're outliers. And then the very tiny babies, like my niece, who was like 2.5 pounds when she was born, they're outliers on the other end, very, very tiny, preemies, right? But most of them are in the middle here, somewhere in the 6, 7, 8 pounds or whatever would be between 2 and 11, sort of in the middle, okay? 2, 11, 13, 6.5. So like maybe this is 6.5 pounds. If it was normally distributed, this middle line would be 6.5 pounds. If this is 2 and that's 11. And when we would run the numbers, if it was normally distributed, meaning most of them are in the middle here, and we get this nice curve of how many are on the light end and how many are on the heavy end, we calculate the standard deviation, and this number will be the mean, the average. And one standard deviation away will capture a certain percentage that are just greater than the mean by that amount. So this graph is made with this number being 1. And I can do this and make our graphs match. I can put a +1 over here. Okay? And I'm going to put a 0 right here. I'm going to put a +2 here. That would be a distance of 2 standard deviations. I'm getting to what that means for us. And then +3 standard deviations. The same thing happens on the other side of the graph, and it's symmetrical. So over here, I have, instead of +1 though, because my 0 scale, my 0 is there in the middle at the mean, this is going to be -1 standard deviation. This will be -2 standard deviations. When I say -2, I'm talking about because there's 1, there's 2. Think of it just like -1 and -2. I go over to the left 2 units. And since I make that middle 0, it's going to be minus 2. Let's get rid of that green stuff or I get too busy. Then I'm out. If I go one more standard deviation out, I'm minus 3 standard deviations. Okay? So now our graph matches this. I have this extra 12 hours in here, this seemingly extra piece of information. Well, since our standard deviation is 2.6 hours, if I go to the right 2.6, I'm going to use a different color here. Let's do this. This is standard deviations. And then down here, I'm going to put in blue 12. I'm going to erase the word hours because it's blocking me up. And I'm going to take 12 and add 2.6. So this plus 1 is at 14.6. This plus 2 is at 2.6. I'm going to get 17.2. If I have three standard deviations, I'm going to add another 2.6 to the one at 2, which is 17.2, and I'll have 19.8. I can do the same thing to the left, but remember I'm subtracting the standard deviation. So 12 minus 2.6 is going to be 9.4. That's here. And then subtract another 2.6 and I get 6.8. And subtract another 2.6 and I get 4.2. So if they talked to 21 students, right? They surveyed 21 students. Let's make it a crazier, larger number so I can work with this density underneath here. Let's say they sampled 210 students, okay? If I had their names in a hat and I drew a name out and it had a name. Actually, I don't even care if it has a name. It has the number of hours they spent that week studying. So I pull a number out, and they're all different, right? But if I pull one out and it's 12.3, well, that one's right here. Let me get a different color so it's a little bit more visible. 12.3. It's somewhere like that. I don't know. I don't have a perfect scale on there. I draw another number out, and it's 11.8. So 11.8 is right there. Now, all the 11.8s are stacked up on top of each other, and there's no spaces, so I would get this kind of thing. I would get a line. If I just identified all the 11.8s, they would be like right there, okay? And there would only be this many, such that the curve would be stacked, go up to the top of that, okay? Now, that's never going to happen with 21 students. It's never going to happen with 210 students. It would be thousands of students, okay, before I would get a very, very nice smooth curve, or it approximates a very, very nice smooth curve. But this height is indicating how many are there. And over here at, what would that be, like 4.4, we only have this many, and the stack is only that high. So remember, in the first 2 weeks, we had some dot plots, and we stacked the points that we plotted, their data points, and we stacked them on top of each other. Think of it like that, except it's so dense, there's no space between the dots. You'd have to zoom in to see any space between the dots, okay? And when you zoomed in, it was actually fill in again, but we won't get too caught up in that. This function, I'll trace it in green. This function, this curve, it's actually a function, like a math equation, okay? And that math equation is governed by a function. We'll talk about that when we get to the normal curve, which is right around the midterm. We'll investigate easier, simpler curves before then to get the idea across. For now, we just need to understand that if I'm at one standard deviation for this data, if I'm at one standard deviation, all the things stacked up at that one standard deviation are 14.6. Okay? If I get a different data set that has a different mean and a different standard deviation, you could use the same graph. My scale might be different. I'm going to make it a little bit flatter because maybe this stuff is more spread out. I'm just going to scratch this one really quickly. Let's say it's the mean height of males in the United States, and I think the average height of men are 5'8", and I have no idea what the standard deviation is. Okay, But let's say 1 standard deviation. When we calculate the standard deviation, we get a number like 2 inches, just to make the math easier for me. Okay, let's say 3 inches. So 1 standard deviation away, we get, add 3 inches, and I get, what is that, 511? Should be using inches, but I don't want to do the math. If I go out 2 standard deviations, this is +1, that's +2. I'm going to go out another 3 inches, which means I'm at somebody who's 6 feet 2 inches. I'm going to go out for 3 standard deviations, I'm going to go out another 3 inches, so it's people that are 6 feet 5 inches. Those dudes are pretty tall, yeah? If I go the other way, to short folks like me, I'm just under 5'8", by the way, so nah. But I'm a big fatso. Don't say anything. I don't know what you'd say, but 5'5", go another 3 inches shorter, and I'm at 5'2", and go another 3 inches shorter, and I'm 4'11". Okay, and statistically, we have approximately the same number of people that are greater in men, United States, greater in height than 6'5", as we do the number of males that are shorter than 4'11", because the area underneath this curve, I'm shading it in blue, represents the number, not really the number, the percentage of data points in those regions. So these are areas, and so this would be some tiny percentage, and this would be some tiny percentage, but they would be equal or approximately equal. That's what the statistics would tell us if we had data that was normally distributed, meaning it fits under some curve like this. Now, the empirical rule, and it's true of any normal distribution, whether it's this one here with a mean of 12 and a standard deviation of 2.6, or a mean of 5'8" and a standard deviation of 3 inches. Okay? Between -1 standard deviation and +1 standard deviation is 68% of the data. Almost 70% of the human males in the United States are between 5'5" and 5'11". Again, those are not real numbers. I made them up, pulled them out of my butt right now. So it's not really those numbers, but 68% would be in between these two standard deviations, -1 to +1. Since it's symmetrical, you could also surmise or conclude that 34% is between 0 and 1 standard deviation. 34% is also between 0 and -1 standard deviation. If you wanted to know the height of 95% of the males in the United States, that's this region. Between -2 and +2 standard deviations, between here and here. And notice how this is just standard deviation. It's not even associated with any specific data because it doesn't matter. Like I said, anything that is distributed normally, and we calculate the standard deviation and the mean, we can draw this graph and draw these lines and know that approximately 95% of the data points are between -2 and +2 standard deviations. -2 and +2 standard deviations. That's what this 95 is telling you. 99.7% of the data points are between -3 and +3 standard deviations. 99.7. So this represents less than 97.35. It's 0.30. It's not exactly that, but less than or equal to 0.15%. Less than 0.15% is less than 411, and I shouldn't put the equal sign there. And this other tail, this right tail, is also 0.15 because there's 0.3 left when I take 99.7, subtract from 100, and it's split equally to this little tiny right tail and this tiny left tail. Okay? So, how do we use this information to do this problem? Now I'm going to focus on this thing. 68% of the students are between what and what? When they're asking about this, they're asking not between -1 and 1. They want you to apply this information, these characteristics of this data to this problem. So we want to know between what and what is 68%. Well, for this, it's 9.4 and 14.6. 68% of the students spent between 9.4 hours and 14.6 hours studying. 95% is between -2 and 2. We calculated that to be 6.8 and 17.2. And then 99.7 is between -3 and +3. That was 4.2 and 19.8. So all you have to do, just sketch a little curve. You could print that out if you wanted to, and just, I don't know, use a whiteboard marker on some piece of plastic, lay on top of it, so if you don't want to print it out 58 times. Or you can just sketch it and just put a 0 there. Put 2 lines that are approximately equally distant from the 0. 2 more lines and 2 more lines. Like, notice this one is taller than this one because my curve isn't exactly symmetrical. You're just getting a sketch so you can put the numbers down. You're just like draw an idea of sketch an idea of what's happening there, and then do the math. Subtract 1 standard, 2 standard, 3 standard deviations. Add 1, 2, and 3 standard deviations by actually adding this number to the previous number when you're going out, or subtract it from the previous number as you're going out to the left. Then you have those down, you can do this problem. This is true. It's going to be true. We're going to run into it again during the semester. Okay? So hopefully this is helpful.